Okay, guys, we're in week 2, module A, and we're going to be talking about load cells. Last week, you guys had a pretty long lecture on strain gauges and how to install them because we had to get the ball rolling, and there's just a lot of steps to installing strain gauges. How do you get 200 people in a matter of a short time to learn how to do this? It takes a lot of time there. And you did good. So let's get into this topic, load cells. You guys are probably used to load cells by bathroom scale. And that load cell in that bathroom scale is just a transducer that converts the forces into electronic signals. Now, what's nice about a scale like this? When you turn it on, you probably aren't going to turn it on and be on it because you need to let it balance out to tear out. So you could use this in one area where if I wanted to have a bunch of bolts that I was going to ship and I knew what one bolt weighed, and I wanted to send 1,000, I could put a box on the scale, tear it out, balance it out. Now I can put the bolts all in there, measure the total weight, and divide it by the individual weight. And now I know how many bolts I have. So I don't have to sit there and count those. In Module B, you're going to be using a load cell that looks much like this one right here. And I want to talk about this load cell. It's poorly designed. And I want you guys to be real careful when you're using it in Module B. This threaded portion right here is connected to the housing. Okay? Down here, there's a line. That's a different housing connected to this thread. What's bad about this design is if we put torque across the load cell from one thread to the next, it'll actually twist and break those fine wires that are hooking up all the strain gauges within this load cell. So we want to be careful in Module B doing that. The load cell that you're going to be using in this lab is a single beam load cell. We're going to talk about that more in detail. There are other types of load cells out there. This one is an S-type. We can mount devices here and down here, and we can pull on it. We have our strain gauges mounted here, and we can instrument that as well, just like all these other gauges. They have a double beam and a round load cell that you guys are going to be using in Module B. Okay, in this lab, you're going to use two different kinds of Wheatstone bridge configurations. Now, before we get into the Wheatstone bridge configurations, I'm not going to go through the derivation of all the equations because we're just going to use the equations that we need in the form to verify what we're going to do in this lab. What am I saying here? Another course that follows us up is we have data AC and basic instrumentation courses that will spend a lot more lecture time. Again, this is just a lab course that will talk about the derivation of all the equations and the equations that you're going to use in this lab. What we're going to do for you is give you the final results, and we're going to have them on the lab sheets for you in terms of equations as to what equations you need to use to measure our volts, gauge factors, etc. So that's going to help you guys out. Now, so this quarter bridge, what's nice about this is it's going to have certified, referenced, let's call it what it really is, resistors that are held to a very tight tolerance. So they're going to be basically the same. So they're probably going to be a little more expensive than if I went out and bought a 120 ohm resistor here. They're going to be a little more expensive because they're better quality of resistor, held to a higher accuracy and tolerance. They're more precise. Because we're using a strain gauge that is very high leveled in terms of precision and accuracy. And those are 120 ohm resistors, remember? And when we pull on that strain gauge, you're going to elongate that gauge area. You're going to see the wires neck down. You're just yielding it, right? We're not going past yield. And so we know Ohm's law that as the resistance goes up, we're going to see the relationship of voltage and current come into play via Ohm's law. And so if we're thinking about that, this one is going to be variable where these are not. So we're going to now see different amount of current flows going through this quarter bridge. We can measure the voltages and the changes in voltages in terms of microvolts. Now let's talk about an advantage to this system. You have one strain gauge, and having one strain gauge, we can put it into an application, a device, and it's very small and discrete. The bad thing about this system is we may have that installed in something, and these resistors, wires going out to the system where the strain gauge is, separated, or even if they're in the same area, temperature change down here, influenced by temperature, the strain gauge and the resistors are going to have different reactions to temperature change. So what we're going to see now is different reactions in terms of current going through those. So now we have a variable. They're not going to be as consistent as maybe what we're going to talk about in a full bridge next. So this is a full bridge Wheatstone. This is what you guys are going to be hooking your load cell up to as one point, and we're going to see the total performance of that load cell. And then we're going to measure the individual performance of each strain gauge. We're going to sum them up. And again, like I said, we're not going to go spend all the time through the derivations of equations, but we're going to be able to sum them up once we check the strain of each of them and come out here and calculate the gauge factor and compare it to our system. And that's going to allow us to be able to put a load on our cell. And when we put a load on our cell, we're going to be able to verify the grams that we're going to get through the controller and see if they compare and match up with what we put on that load cell. So let's look at this full bridge here. Instead of resistors, reference resistors, we went in and changed them out with strain gauges. So we have 4 strain gauges. And again, these are all made to a high tolerance. And so they're all going to be mounted on the same device and out there in the same area. So this is going to take a little more space. You guys know what I'm talking about because you had to mount those strain gauges in lab 1 on first or week 1, and you could kind of see how much space we're talking about. So with these individual strain gauges, we're going to have in the lab R1, R2, R3, and R4. And I tried to keep everything apples and apples in the lecture, the presentation, and how we hook it up, and in the lab sheets. And so everything is going to be referenced in terms of 1, 2, 3, 4, just like this. We're going to use something called a breadboard to run wires. And so let's talk about how we're going to wire this Wheatstone bridge up. I would recommend starting at R1, taking a wire, and you're just going to shoot it over here to R2. Now we're going to take the wire from this pad, we're going to run it down to R4, then we're going to take a new wire from this pad to R3, and then R3 to R1. That's going to give us this nice shape of connections on that. Then we're going to be able to tap off those connections in between R1 and R2, and even here run wires to our unit, and then we can hook that up on the unit as a full bridge, and we can now take our measurements on that with the settings. Watch the lab prep video on how to hook that up. Now, having 4 strain gauges, they're all going to change the same because they're mounted in the same general area, and temperature is going to have less effect on that. So if we see those delta T's, it's not going to change this, and it's going to give us a lot better readings. So again, take note, and good things you need to remember is some of these are going to be in tensile and some of these are going to be in compression. We're going to see that in the next slide here and how that relates to the actual load cell. When we look at this load cell that you're going to be using, you guys are going to be using a single beam load cell. We're going to mount it to this portion of the load cell, and we're going to have another plate mounted to this portion. So we're basically almost kind of like a counterlevered beam, so that when we push down on this load right here, we've got a simulation over here where we fix this in and put a load on it. We're going to come in and put a load on this. We're going to see stresses generated within this area. So this is real common to come in here and precisionally mill this out, keeping the same thickness as here. And what we're going to do is create an area of concentrated stresses in this area, this area, this area, and this area. That's where we're going to mount our strain gauges so we can measure the strain across that area. Now, what we're going to do is go over here and look at something called an FEA analysis. What does FEA stand for? That is finite element analysis. You need to remember that. Finite element analysis. What that does is lets us come in, we can in SOLIDWORKS do this, and actually in Module B, when you guys design your trusses on the second week, we introduce you to FEA, and you guys will be doing this very thing where you can come in and put a fixed condition, and you can apply your load onto this structure, okay? And then what we're going to do is apply a mesh. You know, we're going to tell it what the exact material and the properties are, but we're going to mesh this. Now, what is meshing? That's basically going to set up a series of nodes, little points all through that whole part, 3-dimensionally. And it's going to allow us to connect from node to node and what's happening within each node. And if you were to take a FEA course, you're going to learn there's a lot to different meshing techniques, different types and sizes. And we're just going to go in there and mesh that out to somewhat of a fine mesh. The finer the mesh, the longer the processing time. So now once we have that mesh on there and we have these load conditions, it's going to run a simulation and it's going to calculate all the forces and it's going to give us a plot, and we're going to be able to see some neat things. We're going to be able to see some neat things in this plot. One is it's going to put a scale on the side. So things that are blue down here versus things that are red is going to represent what we call von Mises stress. That's our combined stresses that we're going to have on there. We're not yielding this material, but on this one, we're seeing the red is the highest level of stresses here, the von Mises. And what we're seeing is this area here and this area here and here and here having higher stress levels. What that's telling us, and you can almost tell there's more stress here than here. Okay, we have that set up as a reference dimension within our Wheatstone bridge to kind of compare all these, aren't we? And what we're going to have is here's your strain gauge 1, 2, 3, and 4. And so strain gauge 1 on this beam, the top of it is going to be in tension. Down here, we're going to be what? In compression here. So over here, we're in compression, here we're in tension. So we have different types of loads, and we're going to be comparing those and setting those up in our Wheatstone bridge. So let's kind of sum this up and get you guys ready for lab. Basically, what you're going to do is come in the lab and you guys are going to be assigned that strain gauge unit, a P3, and a breadboard and a series of wires. And you're going to wire them up per the lab instructions and take the voltage and the current settings, and you're going to be able to complete this lab pretty easily in a timely manner. Now, transducers, basically, that's what a load cell is, and we're able to measure those forces. You guys are going to see the different bridge connections from a full to a Wheatstone quarter bridge, and we're going to actually be measuring the strain and the current, the microvolts for each of those. We're going to be putting them in equations, calculating our gauge factors, and we're also going to be able to set it up where we can measure the load on the load cell and calculate that load and verify that the load cell is reading it correctly. And so that last part there, the load cell is a structure that's going to have both tensile and compression in different areas, and that we talked about, and some of them are going to be in tensile, some are going to be compression. I would probably recommend going back and looking at that graph and kind of associating which areas are in tensile and compression. That might be a great quiz question. So at this point, you guys should be ready for lab, and we'll catch you in lab.